is the 24th lecture, Introduction to Laplace Transforms. I have covered a part of it intentionally. I will show you the picture of Laplace a little later. This contains the picture of Laplace. And our topic today is Introduction to Laplace Transforms. And the motivation for Laplace transforms comes in the following manner. The success of Fourier transform is due to the fact that most practical signals and arbitrary practical signals in many cases can be decomposed into a superposition of exponential signals like this, where S sub I is j omega I. S sub I is j omega I. Many practical signals can be decomposed like this. This is the first reason why Fourier methods are useful or successful. And the second reason is, there are two reasons. Second reason is that e to the st is an eigenfunction of LTI systems. That is, if you feed a signal of e to the st to an LTI system, then the output is h of s e to the st. The output is of the same form except for a multiplying factor. These are the two reasons why Fourier methods are useful in the analysis of linear time invariant systems. Of course, with s equal to j omega, and the interpretation is that h of j omega, which we, for simplicity, all the while we have been writing this as h of omega, is the frequency response of the system, and the Fourier transform of x of t, Fourier transform of x of t represents the spectrum or the frequency content of the signal. Now, in Laplace transform, what we do is we generalize this concept and do not restrict s to purely imaginary. We make small s a general quantity which has a real part as well as an imaginary part. And we shall see that this generalization expands the domain of signals and systems which can be treated analytically with ease, and this is a very simple modification, and this was introduced by this man Laplace, whose first two names are Pierre Simon Laplace. He showed that if you generalize s to sigma plus j omega instead of simply j omega, then the restrictions on the convergence of transform, that is Fourier transform convergence, and the analysis of linear systems with initial conditions becomes greatly relaxed, and it can be done in situations where Fourier transform fails. We shall show several examples where Fourier transform fails, but Laplace transform does the work. This is the picture of Laplace that I could find out from one of the textbooks. Well, I have enlarged it. It doesn't look quite nice, but his name was Pierre Simon Laplace, and the title Marquis de was given by one of the politicians. The Laplace was a French astronomer by training and by love of subject. He was an astronomer first and then a mathematician. He is credited with the transform that bears his name, Laplace transform, which has revolutionized the analysis of circuits and systems with non-sinusoidal inputs. With sinusoidal inputs, Fourier transforms does wonderful job. You can even avoid Fourier transform. You can go to phasors and carry out the job. But Laplace transform is the most general tool known for analyzing linear time invariant continuous time systems. This I must point out. This is not a transform for discrete time systems. He is, however, better known for his book on celestial mechanics, which is his masterwork, which summarized the achievements in astronomy from the time of Newton. There are many original contributions, and as you will know in a little while, Laplace worked under various governments, 3 successive governments, and he shifted his political allegiance very rapidly depending on who is in power. And in the time of Napoleon had asked him if God had helped him in bringing out his hypothesis, and Laplace's reply was, there was no need for God in my hypothesis. This sentence has become very famous, and Laplace is always coupled with this sentence, there was no need for God in my hypothesis. That is, well, it is also typically signifies how arrogant and a bit snobbish Laplace was. Thankfully, he's dead long time ago. You would not be able to counter what we are saying now, but it has been recorded. He was born in a small village, in a small town, Beaumont, in Normandy province of France. Little is known of his early life, except that his father was a poor farmer. That's all that is known, because the snobbish Laplace, after he became famous, did not like to speak of his humble origins at all. He never mentioned his origins. Rich neighbors, it is said, recognized his talent and helped finance his education, first at Caen and later at the military school in Beaumont. Through the efforts of the famous physicist D'Alembert. Have you heard his name? Yes, sir. D'Alembert is famous in acoustics, vibration of strings. That's where D'Alembert made his name. He was very much impressed by his abilities, and with his efforts, Laplace became a professor of mathematics in Paris at the age of 20. He was an opportunist, shifting his political allegiance as required, so that his career successfully spanned 3 regimes in revolutionary France. The Republic first, then the Empire of Napoleon, and finally the Bourbon Restoration. Napoleon made him a count and Louis XVIII made him a marquis. His mathematical abilities, however, were genuine, inspiring the great mathematician Poisson, you must have heard his name also, Poisson, to level him as the Isaac Newton of France. It is his work that we are going to study in the simplest possible manner. If we go back to the to the question of a signal of the form e to the st, which is applied to an LTI system, and the output is h of s e to the st, then you know that h of s is integral minus infinity to infinity h of t e to the minus st dt. This is the general eigen value for the linear time invariant systems, where small h of t is the, what is h of t? The impulse response of the system, and capital H of s is the frequency response. And in Fourier transforms, in Fourier analysis, we had constrained small s to be equal to j omega. Now we extend the concept of s to sigma plus j omega. Naturally then, because s has a real part and an imaginary part, it shall require a 2-dimensional space to describe a point. In other words, we shall have a space, we can have the rectangular coordinates, or we can have the polar coordinates, which shall have sigma on one of the axes and omega on the other axis. Convention is that we don't simply write omega, we write j omega to indicate that this vertical axis is the imaginary axis. So any point in the S plane, has 2 coordinates, the real part and the imaginary part, and the imaginary part is the length of this, the real part is the length of this, all right. So any point S, as you know in the theory of complex variables, this is called what is it called? Argand diagram, as it is called, and this is the S plane, and we shall have lot to do with the S planes. Previously in the Fourier transform we had been in the S plane, but we confined our attention to a line, that is the j omega axis. We didn't shift either to the right or to the left. It is also clear well, it is at this point that we define the we define Laplace transform formally, that is, given a function x of t, the Laplace transform of x of t is defined as, if it exists, the question of existence shall have to be addressed to with some more care than we did in the case of Fourier transforms. But then you will see that the convergence is much more relaxed as compared to Fourier transform. Well, we define it as minus infinity to infinity x of t e to the minus st dt, and symbolically we write this as x of t. To indicate that this is Laplace transform, we write a script L here and write capital X of s, that is x of t and capital X of s are Laplace pairs, and this mapping from the t domain is a single dimensional domain to S domain. S is a two-dimensional plane, two-dimensional domain, is also unique. That is, if x of s exists, if the Laplace transform exists, then this transformation must be one-to-one. It must be unique transformation, and then we can come back from capital X of s to x of t. This is what I mean by this double arrow, that we can go from t to s and s to t. It is also clear that if sigma equal to 0, that is, if we confine our attention to the j omega axis, then obviously Laplace transform should be the same as Fourier transform, provided both exist. All right. For sigma equal to 0, Laplace transform is the same as Fourier transform. In other words, capital X of s for s equal to 0 is the Fourier transform of x of t. I have written the same thing in an equation form. It also follows that capital X of s not equal to 0, I beg your pardon, not s equal to j omega, s not equal to j omega. All right. The first one is x of s with sigma equal to 0, the real part equals to 0, real part of the variable equal to 0, that is, we are confined to the j omega axis, is simply the Fourier transform, provided it exists. Existence is being implicitly assumed in these relationships, otherwise this relation is not valid. If it does not exist, there is no question of an equation. The second equation is that capital X of s, if s is not equal to j omega, by definition you see it is minus infinity to infinity x of t e to the minus st, which I can write as e to the minus sigma t multiplied by e to the minus j omega t dt. And you notice that if I define a new function of time as x of t times e to the minus sigma t, then obviously capital X of s in general, which is the Laplace transform, can be written as the Fourier transform of this new time function, that is x of t e to the minus sigma t. Is that clear? The Laplace transform can therefore be viewed as the Fourier transform of the original function multiplied by a factor. And there are many situations in which if this factor is not there, the Fourier transform does not exist. Is the point clear? If Fourier transform of x of t may not exist, but Fourier transform of x of t e to the minus sigma t may exist for constrained or restricted values of sigma. That is, for some values of sigma this may exist. All right. For sigma equal to 0, the Fourier transform may not exist. What is the message that I am trying to convey? I am trying to convey that Fourier transform of a function may not exist, but Laplace transform exists. And if Laplace transform exists, what does the existence mean? If we go back to the to the definition of Laplace transform, that is capital X of S is minus infinity to infinity x of t e to the minus st dt, and we have said that x of S is the Fourier transform of x of t e to the minus sigma t. Well, what does the existence of x of S mean? It means that x of t e to the minus st is absolutely integrable. This is the condition for the existence of Laplace transform. Now, the mod of x of t e to the minus st, isn't it simply x of t e to the minus sigma t, the mod of x t e to the minus sigma t? And therefore, what in a sense it means is that adding this factor, not adding, multiplying x of t by this factor helps this integral to converge, and therefore this factor sometimes is known as the convergence factor. E to the minus sigma t is a convergence factor. Now, naturally, the convergence shall depend on the value of sigma. It may be such that if sigma is positive, definitely there is a possibility of convergence. As t tends to infinity, it goes to 0. Not necessarily though, because t also can go to minus infinity, lower limit. And therefore, for some values of sigma, what does that mean? For some values of sigma, that means for a restricted part of the S plane. Sigma is after all the real part of S. Alright. So, for some values of sigma, x of S may converge, for some others it may not. This question of convergence we shall take up formally a little later, but what I am trying to convey to you is that there are functions for which Fourier transform does not exist, but Laplace transform exists. For example, one of the functions is ut. The Fourier transform of ut in the conventional sense does not exist until you admit the existence of delta omega, and you know that the Fourier transform of ut is 1 by j omega plus pi capital, which is 1, times delta omega. Alright. So, it is simply 1 by j omega plus pi delta omega. This requires the definition of delta omega. On the other hand, if we come to Laplace transform, because of this convergence factor e to the minus sigma t, it is simply 1 by s. The Laplace transform is simply 1 by s. You do not require a delta function at all. Alright. And this would be true for real part of s greater than 0. That means there is the values of sigma is restricted to be strictly positive. Is that clear? The value of S is strictly restricted to be positive. That means there are regions of S plane where the Laplace transform converges. At other places it does not. And therefore, this is one fundamental difference between a Fourier transform and Laplace transform. For Fourier transform, you do not have to specify any value of omega. You do not have to specify, because Fourier transform exists if it exists. When it exists on the j omega axis of the S plane, it is on this axis that Fourier transform exists. On the other hand, for Laplace transform, there are regions of the S plane where it exists, there are regions where it does not converge. And therefore, in Laplace transform, not only the transform is important, but the region in which it exists or it converges is also important. And therefore, whenever you specify x of s, you must also specify not only the expression for x of s, but you must also specify the region of convergence or ROC of this x of s. We will come to a few examples, and then we will explain what the properties of the region of convergence is. The question of convergence must be understood very, very carefully, because this is one thing that distinguishes Fourier transform from Laplace transform. Laplace transform has 2 degrees of freedom, sigma and omega, whereas Fourier transform just 1 degree of freedom, omega. Let us take an example. Let us say e to the minus at ut. Let us say this is my x of t. Then you know that the Fourier transform of x of t is simply 1 by a plus j omega. Now, what is the restriction on omega here? Is there any restriction on omega? No, there is no restriction, but there is a restriction on a. A must be greater than 0. A must be, first thing is it must be real. If it is not real, then real part of a should be greater than 0. All right. Now, let us try the Laplace transform. The Laplace of x of t is equal to minus infinity to infinity, well, e to the minus at, then we should have e to the minus st, which is e to the minus sigma t, e to the minus j omega t dt, and therefore this is minus infinity to infinity e to the minus a plus sigma t ut, and therefore we take this as 0 to infinity. All right. So, this lower limit becomes 0, and we have e to the j omega t minus dt, and exactly in a similar manner as in the Fourier transform case, we can evaluate this integral as Laplace of x of t is e to the minus at ut, it is a plus sigma plus j omega, provided a plus sigma is greater than 0, all right, which I can write therefore as a plus s, because sigma plus j omega is nothing but s. And this expression I can write as a plus real part of s greater than 0. That means the real part of s is greater than minus a. All right. Now, let us look at what this means in the form of a picture. E to the minus at ut, and we have shown that capital X of s is 1 by a plus s with real part s greater than minus a. Let us look at the picture. In the s plane, this is sigma and this is j omega, and suppose a is positive. A had to be positive for Fourier transform to exist. So, suppose a is positive, then minus a obviously is somewhere here. And you see, real part of s greater than minus a means that if you draw a vertical line, if you draw a line parallel to the j omega axis, then it is this Fourier, this Laplace transform capital X of s equal to 1 by a plus s shall exists only for real part of s greater than equal to a. That means in the plane to the right of the vertical line s equal to minus a, sigma equal to minus a. All right. So, it is the total region, it is an infinite region over which the Laplace transform exists, but there is an infinite region to the left of minus a where it does not exist, and therefore, along with Laplace transform, it is extremely important that you specify what the region of convergence is, the ROC, and we derived it very simply from considerations of Fourier transform. Fourier transform existed for a greater than 0, and therefore, Laplace transform exists for a plus sigma, because the real part is added to a greater than 0, which translated into this consideration, that is real part of s greater than minus a. Now, obviously in this, if you put a equal to 0, if you put a equal to 0, then it is simply the unit step function, and you see nothing, no modification is needed here. You put a equal to 0, therefore x of s is 1 by s for real part of s greater than 0. That means this would be the open right half s plane. Let's understand what I mean by this. What I did was x of t equal to ut gives me capital X of s equal to 1 by s. I had put a equal to 0 with real part of s greater than 0, which means that if I look at the s plane sigma j omega, then my real part of s, that is sigma, has to be greater than 0, which means the right half of the s plane, the middle line is the j omega axis. Now, the right half of the s plane, what happens to the j omega axis? it can be claimed by the right half plane as well as the left half plane, because it is a boundary. It is the transition region between the left half plane and the right half plane, HALF half plane. When I include in the right half plane the j omega axis, then we say it is a closed right half plane. That means it is closed on this side. On the other hand, if in this definition real part of s greater than 0, it is the open right half plane, because sigma equal to 0 is not included. You can come very close, infinitesimally close to the j omega axis, but not include it. You understand what we mean by closed RHP, right half plane, and open RHP. Open RHP sigma is strictly greater than 0. Similarly, open LHP sigma shall be strictly less than 0. Is that point clear? All right. And you see, we didn't have to do any artifice of a delta function to define or to get the Laplace transform of a unit step function. Suppose there is a function x of s which converges. Suppose there is an x of t whose Laplace transform is x of s, follow this point carefully, which converges for, let us say, real part of s greater than a, where a is positive. All right, which means that the region of convergence is, there is an a somewhere here, there is an a somewhere here, and the region of convergence is this. This is the j omega axis, this is sigma and this is j omega. Now, what can we say about x of t and its Fourier transform? Obviously, Fourier transform for x of t shall not exist, does not exist, because the region of convergence, that is the region of S in which x of s converges, does not include the j omega axis. If it includes the j omega axis, we can confidently say x of t has a Fourier transform. Is this clear to you? That the region of convergence clearly shows whether the function is Fourier transformable or not, and we shall come to an example of this a little later. Let us consider now another important aspect. I have said that if x of t is x of s, then x of s has to be specified along with its ROC, along with its region of convergence. We will now take an example in which the x of s is the same for two functions, two different functions, but their ROCs are different. For example, let us take x of t as minus e to the minus at u of minus t. What kind of a function is this? Obviously, it exists for t less than 0, it exists for t less than 0, and it is a negative function. That means it is minus 1 here, minus 1, and then it goes to 0 as t goes to infinity. This is the function, an exponentially rising function or decaying function. All right, I leave that to you. Now, x of t is minus e to the minus t u of minus t, and therefore capital X of s, if it exists, has to be minus u of minus t, and therefore I start from minus infinity and I go to 0. All right, e to the minus at, then e to the minus st dt, and you can see that this is minus infinity to 0, e to the minus a plus sigma t, e to the minus j omega t dt, and for this to converge, for this integral to converge, what restriction do we need on a plus sigma? A plus sigma must be less than 0. Why? Because t itself is negative, and therefore the product a plus sigma times t must be positive in order that this integral converges. And you can show that this is exactly equal to 1 by s plus a. alright. By carrying out this integral, you can show that this is 1 by s plus a, where a plus sigma has to be 0. In other words, real part of s must be less than minus a, alright. So, we have now, if I summarize this, x of t equal to e to the at ut, capital X of s is 1 by s plus a, provided real part of s is greater than minus a. And the other function is x of t is minus e to the minus at u of minus t. X of s is the same 1 by s plus a, the expressions are identical, but now the region of convergence is real part of s less than minus a, alright. This is also e to the minus 80, yes. I am sorry, I made a mistake. Both are e to the minus 80 ut, alright. Now, in terms of a picture, you see the region of convergence here is sigma j omega, sigma j omega. The region of convergence here is to the right of the line s equal to minus a, and the region of convergence here, if a is positive, then minus a is somewhere here again, and the region of convergence is this, to the left of this, alright. So, the ROCs are completely different, although the expressions are the same, and therefore, if I simply ask you, find out the time function corresponding to a given expression, well, you will not find out a unique answer. A unique answer is obtained only when the ROC is also specified, and this is what complicates Laplace transform analysis a little, but the advantages that are obtained by generalizing j omega to sigma plus j omega are too many, and therefore this complication is no complication, is not counted as a complication. Now, let's say our given function x of t is, let's say, a combination or a superposition of two functions, x1 of t and x2 of t. Obviously, Laplace transform is a linear operation. Why? Because integration is a linear operation, and therefore capital X of s shall be capital X1 of s plus capital X2 of s. Now, we have a problem, because the ROC of X1 of s is ROC1 and the ROC of X2 of s is ROC2. So, what is the ROC, region of convergence of X of s? It must be the common part of ROC1 and ROC2. How do we show that? Inverted U? Is that the correct one? Okay. So, the ROC is the intersection of the two. To take an example, let us consider x of t as e to the minus t ut plus e to the minus, let us say, 5t ut. Then capital X of s is 1 by s plus 1 plus 1 by s plus 5, and the ROC of this is real s greater than minus 1, and the ROC of this is real s greater than minus 5, and therefore the ROC of capital X of s is real s greater than minus 1. This is the intersection. This must be remembered, that if you are superimposing various functions, then the ROC is the intersection of the ROCs of individual functions. Let us consider this example in little more details. X of t is e to the minus t ut plus e to the minus 5t ut, and we said capital X of s is equal to 1 by s plus 1 plus 1 by s plus 5 with real part s. Now, we don't write the ROCs individually, we just write the ROC of the total X of s, that must be greater than minus 1. Now, you can write this as a rational function like this. You recognize that this is in the form of a partial fraction expansion. If you combine the two, s plus 1, s plus 5, and you shall have 2s plus 6, this can be written as 2 s plus 3 s plus 1 s plus 5. And for most of the functions that you shall encounter in linear system analysis, lumped systems, the x of s or the Laplace transform shall usually be of this form. That is, it shall be of the form of a polynomial divided by a polynomial. P of s divided by q of s, the name for which is a rational function. That is, capital X of s usually shall be a rational function. Now, a rational function like this or improper. It could be proper or improper. It doesn't matter. Well, let's consider a proper rational function. All right? Let's consider a proper rational function. We will come back to improper a little later. Now, values of s for which x of s is 0, obviously x of s will be 0 if the numerator vanishes. That is, if p of s equal to 0. And these values of s are called the zeros of x of s. All right. For example, if p of s0 equal to 0, some s0, then obviously x of s0 is also equal to 0 unless q of s0 is also equal to 0. Well, now we come to proper, improper, and prime and non-prime. If there is a value of s0 at which the numerator as well as the denominator vanish, what does it mean? It means that s minus s0 must be a factor of p of s and also q of s. So, p of s and q of s in that case therefore are not relatively prime with respect to each other. That means they are non-prime. If you discover that there are non-prime factors, then it is most convenient to cancel them to start with. That is, you consider x of s which is relatively, in which the numerator and denominator are relatively prime with respect to each other. What are such rational functions called? Well, we will come to the name later. There is no specific name, we will have to give a name. But let it be understood that the kind of rational functions that we are considering, the numerator and denominator are relatively prime with respect to each other. Then wherever the numerator vanishes, the whole function vanishes. All right, and such points are called zeros of the function, and in the S-plane they are represented by circles like this, small circles. This is a point S0 at which the function vanishes, and therefore it is indicated in the S-plane by means of a circle. On the other hand, x of s equal to p of s by q of s, if there exists an s equal to s1, suppose q of s1 is equal to 0, but not p of s1, not p of s1. That means p of s and q of s are primes, are relatively primes with respect to each other, then obviously the function blows up. That means x of s goes to infinity. Can S1 be in the region of convergence? No, because in the region of convergence the integral converges to a value less than infinity. That is, the integrand is absolutely integrable, and therefore S1 cannot be in the region of convergence. Such points in the S-plane are called poles of the function x of s. So, any rational function can be described by zeros and poles. If we know the zeros and poles, then we know the rational function, except for a constant, a multiplying factor. For example, the previous function that we had was capital X of s was equal to twice s plus 3, s plus 1, s plus 5. We have here 1 0 at s equal to minus 3 sigma j omega. We have a 0 at s equal to minus 3. We have a pole at s equal to minus 1, and the poles are denoted by crosses. So at s equal to minus 1 there is a pole, and there is also a pole at s equal to minus 5, all right. So we have 2 poles and 1 0. Except for the multiplying constant 2, if you are given this picture, then you can write down the function immediately. You can write x of s, if simply this picture is given, then you know x of s shall be of the form s plus 3, s plus 1, s plus 5 multiplied by some constant k. So you need some another data to be able to find out k. For example, x of 0 may be given to you at s equal to 0. If x of 0 is given, then obviously you can find k. We go back to the question of poles and zeros. I hope you have come across these terms earlier, poles and zeros, alright. Then my question is appropriate. Is it proper to say that this rational function capital X of s has only 1 0 and 2 poles? We don't need a God in any hypothesis or any law. Well, in general, the correct statement is any rational function has equal number of poles and zeros. The number of poles must be equal to the number of zeros. The only difference is here the other 0 is at infinity. You see, the degree of the numerator is 1, the degree of the denominator is 2, and therefore when s goes to infinity, capital X of s goes to 0. How do I show infinity? I make a break here, then go as far left as I can go, and show a 0 here, and I call this infinity. Well, obviously I should show minus infinity. Question arises, philosophical questions, they are of no consequence as far as system analysis is concerned. Why do you show it at minus infinity? Why is it on the why is infinity on the real axis? Why don't you show it at plus infinity? Why don't you show it as plus j infinity or minus j infinity? Point of fact is that infinity is considered as a single point. Since we don't know where it is, it's convenient to consider it a single point, and it coincides with the concept of Brahma, that whichever way you go, you reach a single point, alright. So we should not extend this analogy.
But why minus infinity? You usually take it to the plus infinity.
You will see later why minus infinity. It's a matter of convenience. Taking it at minus infinity, for example, in circuit theory helps us. RC networks, for example, have their poles and zeros on the negative real axis. They cannot have on the positive real axis. And therefore, the 0 at infinity, if it is there, or pole at infinity, if it is there, must be on the negative real axis. The RC networks cannot have poles and zeros anywhere else. They must all be on the negative real axis.
So suppose you have coincident poles and zeros, then how do we depict the picture?
If we have coincident poles and zeros, why? Okay, that is a good question. Suppose I have s plus 1, s plus 3, s plus 2, s plus 1. There may be a system in which this happens, that a pole and 0 coincide. Alright, then what we show is in the form of a picture. If you can discover this, we may not be able to discover this because in the analysis you might have tacitly, implicitly cancelled it. Alright, if we discover this, then we show a 0, and on this we show a pole. Such an overlapping pole and 0, if it exists, then this pole or 0, you know, pole is a singularity. Does it make sense? And a complex variable. This singularity then becomes unobservable. That means whatever you do to the system, you cannot find a response which reflects the existence of a cancelling pole and zero. Let me give you an example.
Suppose we have s plus 1 whole square in the denominator.
Suppose you have s plus 1 whole square in the denominator. Well,
and not in the numerator, s plus 1.
okay, then you cancel out 1.
No, suppose we have s plus 1 square in the denominator and not in the numerator.
Okay, that's a good question. All right, then you show double pole. And you show 1 0. Now, if it is a 20th order 0, for example, obviously we cannot go on drawing 20 circles. So what we do is we simply say 0 multiplicity mult is equal to 20. Just like if you differentiate a function 20 times, you don't put 20 dashes. What you do is d of superscript 20. So this is the way. But let me give you a challenging example. A very simple circuit. All right, we have an R. I don't know if you have come across this. A resistance, an inductance L. Then we have a resistance R and a capacitance C, where the value of this inductance is equal to C R squared. You can show that the input impedance is equal to capital R. Simply capital R. The existence of the inductance and the capacitance, the two arms, they produce a cancelling pole and zero. And therefore, this, for example, has a 0 at minus R by L. It cannot be observed at all. And if this is, now let me use color. If this is enclosed within a black box, which I have shown by outline, all right, it's a black box, and I enclose another resistor, a pure resistor R, in another black box, and the boxes are indistinguishable from outside, there is no way on earth that you can distinguish between the two boxes. Which one contains two resistors and which one contains one resistor, you cannot do. There have been many controversies about this in the early 1900, let's say up to about 1931 or so. There have been many people who have said this was a challenging problem in circuit theory, who have said, yes, I have discovered a method. I feed some noise into it, but after all calculations he finds out that the noise content is the same. There is, if they are enclosed in a black box, you can say, well, if the black box is non-magnetic, it is shielded, let's say, the black box is shielded, so that you cannot discover by bringing a magnet and inducing something in the inductance and so on. It's a situation where there are unobservable modes, unobservable singularities. If that occurs, then you can do nothing about it. Next we come to the question of, have I already said that Fourier transform may exist? I give you an example, isn't it? Fourier transform does not exist, but Laplace transform exists. If the ROC is, let's say, does not contain the j omega axis, all right? If the ROC does not contain the j omega axis, then Fourier transform doesn't exist, Laplace exists. If t does not exist, but Laplace transform exists. Well, this, as I said, makes life very interesting, because there are, you can expand the range of functions which can be dealt with by Laplace transform. And it brings us to one particular question, that is, what should be, in general, what should be the shape of the ROC of a Laplace transform? Obviously, the ROC shall be bounded by vertical lines, that is, lines parallel to the j omega axis. Now, can you give an argument or a proof that it cannot be an arbitrary shape like this? The ROC cannot be an arbitrary shape like this. I claim, I hypothesize without God, that the ROC must be bounded by lines parallel to the j omega axis. This is my hypothesis. Can you give an argument or a proof? You see, what do you mean by the ROC? you know that x of s, very simple proof, we have already done this. X of s is Fourier transform of x of t, x of s is Laplace transform e to the minus sigma t. Now, in this Fourier transform, j omega does not occur at all. That is, the vertical coordinate is not of any concern. It only depends on sigma, and therefore, the ROC must be bounded by lines parallel to the j omega c. Omega can take any value. It is only sigma on which the ROC depends, and therefore, the ROC must be strips. Well, when you say ROC is like this, it is a strip from the two-dimensional plane bounded by a line parallel to the j omega axis. The only difference is an infinite strip. There can be situations in which the ROC is like this. It can be like this. Let us say this is sigma L and this is sigma R. All right. It may be bounded between two sigmas. Sigma R is negative, this is 0, and this is sigma L. Obviously, for such a situation, the Fourier transform exists because it includes the j omega axis. ROC is not necessarily infinite, it can be finite also. To show this, we have to consider three possible cases. Let us consider only one of them today. We will consider the other two next time. Suppose we have an x of t which is finite, that is, it exists over, let us say, a finite region of the t axis. X of t, let us say this is capital T1 and this is capital T2. That is, x of t is a function f of t multiplied by a gate u of t minus T1 minus u of t minus T2. All right. And it says that if the Laplace transform of this converges for some sigma equal to sigma 0, let the Laplace transform of x of t converge for some sigma equal to sigma 0. What is the Laplace transform? It is minus T1 to T2 x of t e to the minus st dt. It converges means what? It convergence means integral T1 to T2 mod x of t e to the minus sigma 0 t dt shall be less than infinity, right? My hypothesis, now I state the hypothesis, that if x of t exists over a finite range of t and its Laplace transform converges for some sigma equal to sigma 0, then I state that it converges for all values of sigma. That means the entire S plane is its region of convergence. And to show this is extremely simple. What we have said that by hypothesis T1 to T2 xt e to the minus sigma 0 t dt less than infinity, because the Laplace transform converges for some sigma equal to sigma 0. Let us take a general sigma. Then integral T1 to T2 xt e to the minus sigma t dt for a general sigma which is not equal to sigma 0. This can be written as T1 to T2 xt, look at the argument. We write this as e to the minus sigma 0 t dt, then we make the correction. What do we get? E to the minus sigma 0 t. Is that okay? All right. Now we consider, obviously you have to consider two cases. One is sigma greater than sigma 0 and sigma less than sigma 0. Now if sigma greater than sigma 0, if sigma is greater than sigma 0 and we call this integral as capital I, then obviously capital I is equal to T1 to T2 xt e to the minus sigma 0 t dt let us go back to this integral. I have considered sigma 0, sigma to be greater than sigma 0, alright. So, this quantity is positive, right, this quantity is positive. What is the highest value of the integrand? When does it reach the highest value? Obviously when small t, no, highest value, small t is equal to capital T1. It is a range, 0 may not be included. T1 may be a negative quantity, then obviously the lower limit, agreed? And therefore, capital I should be, if I take this exponential factor outside and put small t equal to capital T1, then obviously e to the minus sigma 0 capital T1, alright, then obviously this equality sign shall be less than equal to, alright, and since sigma is greater than sigma 0 and this is less than infinity, by definition the Laplace transform converges for some sigma equal to sigma 0. So, this is less than infinity, this is also less than infinity, and therefore the whole thing is less than infinity. In other words, any point sigma greater than sigma 0 is also in the region of convergence. And in a similar manner, you can show that any point sigma which is less than sigma 0 also is in the ROC. And therefore, the argument is that the whole S plane is the ROC. The sum and substance of the story is, if you have an xt, defined over some finite region of t, and if the Laplace transform exists at any point in the S plane, if the Laplace transform exists, it may not exist, why not? You could have a function which goes like this, the function itself blows up, then of course you will not have a Laplace transform, right? So, if the Laplace transform exists at any point in the S plane, then it exists at all points in the S plane, alright. So, for a finite duration signal which is well behaved, what does well behavior means? Qualitatively, it does not blow up anywhere. For a finite duration well behaved signal, the complete S plane is the ROC. What does that mean? It means that capital X of S shall not have any pole, it shall have only zeros. We will consider the other two ramifications of this property next time.